right. Record, so that means it's real. So yes, welcome back. Happy Garbage Day. I've got my merch on. I'm the only person in the world with a Happy Garbage Day t-shirt. It's mine. And the back, of course, lisahoffman.com. But we're talking about the homework system and how it is generating error messages when you try to connect sometimes. So I apologize for how annoying that must be. I cannot fix it without potentially breaking it, and I'm hesitant to try to fix it and inadvertently break it in the middle of the semester. But what you can do is clear your cache for your internet browser and your history. If that doesn't work, switch to a different browser than the one that you normally use. I've been able to switch over to Edge and manually redirect it to HTTP as opposed to PS, which is what it wants to do it, and that has worked. So if you get stuck on none of those work, please let me know, and I will try to keep digging throughout internet advice on how to temporarily fix this. It may be the case that you use one browser that has lower security settings just to do homework, but you don't use it for anything else that you would do with respect to entering sensitive information. I'm not collecting credit card numbers or anything that would, you need to worry about. I'm not going to sell your IDs online or, anything crazy. So I'm aware of the problem. I apologize. We're trying to make it work for the next couple weeks or so. Because that's all we have left, folks, is 3 weeks of classes. Can you believe it?
Yeah.
We are in the home stretch. Next week we have a week off, which will be nice. And you can be working on homework 4 if you haven't had a chance to get started on that. As I warned you, it's complex, but there's nothing in it that we haven't talked about at least a little bit. If you get stuck on something, please let me help you. I have office hours tomorrow as usual, and you can email me questions at any time, and I'm happy to help you troubleshoot. Right now what we have to do is formative assessment number 6, our second to last one of those, so I thought we could start by going over that. Let me get the screen share going so the Zoomers can see where I'm at. So this is a traditional one in terms of just reviewing concepts and vocabulary. So first question here, with respect to the process of starting to enter time invariant predictors, why is it important to establish the best fitting unconditional model for time before examining other predictors of interest? That's my question. And I read all of the answers this morning and updated grades accordingly, so I know that everybody wrote something down. Who would like to tell me what you said? Who's feeling brave today? Zoomers, as usual, I'm watching for the chat window, or you can just talk to me. We have 5 roomers and, 6 Zoomers today? What do you think? What did you write down? Why do we worry so much about time first? What do you think?
Yeah, one of the things that I wrote was that based on the model that we have for time and the fixed and random effect that we included, we will interpret the role or the usefulness of the other predictors, especially those at level 2, and what kind of variance can we explain, for example, with the main effect of a level 2 predictor or the interaction or a cross-level interaction. So this is like the first step to include more predictors.
Yeah, so to summarize, my version of that would be that the model for time dictates what roles your level 2 predictors have to play. So you can always put in a main effect of a level 2 predictor, and that would then describe intercept differences. But what else they would have to do is going to be dictated by your model for time. So for instance, let's say that we had just 3 occasions. We have, say, a random linear model for change. In that type of model, with a random intercept and a random linear time slope, how many different ways do people differ from each other? If that's my model. Not a trick, I promise. Just 2, right? So we would potentially have a main effect of a time invariant predictor that could account for random intercept differences. We could also have a predictor by linear time interaction that would then account for time slope differences. What if instead I had a piecewise model? So let's say that I have at least 4 occasions. I wanted to have, say, an early practice slope and a later practice slope, something like that. If both the slopes were random, then how many ways do people differ from each other? Yeah, not a trick, I promise. If I have two random slopes and a random intercept, how many ways do people differ from each other?
3.
3. So that means each time-varying predictor can do how many things? 3. What if we have a quadratic model? We have individual differences in linear change and quadratic change. Then how many ways can a time-invariant predictor help us? 3. So yeah, to me, the idea of modeling time first is both conceptual and statistical. The conceptual part is knowing how many ways people differ from each other then dictates how many different roles any person-level predictor is going to play. Ultimately, the goal of a person-level predictor is to explain why people differ from each other. But what we need to know is how many ways do people differ from each other. So that's one. Some of you wrote about the relative amount of variability. So between persons versus within persons. If more of your variability is between persons, then you know that time-invariant predictors are going to be more important for predicting that variability relative to time-varying predictors. Another one you can think of is how the people in the statistics or biostatistics department might talk about this same question. Tell me about person dependency. What's that? If I say that we have dependent data, what's the concern? What's dependency mean?
Correlated outcomes.
Yeah, correlated residuals. Yep, but you can correlated outcomes is close enough. And if we're going to appropriately model person dependency, that means that we have to build into the model all of the reasons why the residuals would have been correlated. The random effects, the between person differences that we put in are the reasons in most cases. We can then also let the residuals have whatever remaining correlation pattern that they need to. So getting the person dependency correct then should help us make correct inferences about the significance tests of the slopes for our predictors. Otherwise, the standard errors for those tests could be either too big or too small, depending on how we've screwed up the model. So a second reason then, besides just dictating what are the ways that people differ from each other to be explained, in order to believe the tests that we put in the model for those slopes, we want to make sure that we have all of the person dependency appropriately characterized. Person dependency with respect to time is going to be the lion's share of what we have to worry about, but that's not everything. Where we are headed in the next semester, if you're able to come and stay with us, is talking about how to model effects of other kinds of time-varying predictors besides time. So for instance, if I ask you every day, how healthy do you feel and how stressed do you feel? Some of us will have different slopes relating how our stress is related to our health. Some people might have flat slopes, meaning I am fine no matter what, and the rest of us are like, stress is bad for my health, and I have significantly negative slopes instead. So that could be yet another way that people differ from each other, is in their reactivity to time-varying predictors. So that then creates another source of person dependency, not with respect to time, but with respect to stress as another level 1 predictor. So the same ideas show up again in the context of other types of level 1 predictors, but modeling dependency so that we can trust the answers is the big part. Yeah, I think those are the main things. Did I miss anything? Anything else that folks wrote down that I'm not thinking of or haven't said yet? No? We're good? All right. Then next one, an easy one, synonym time. Give me all the words you can think of that go with level 2 predictor. There's one, time invariant. What else?
Person attribute. Person characteristics.
Person characteristics. Yeah, I'll take that.
Grouping variable. What do you think?
If it's way peoples differ from each other, like if it's a constant group, then yes. If it is a group that you can move in or out of as time goes on, then no. But most of the time, groups are person things. For instance, if I were to go to like a support group, and I pick which support group I go to based on what my schedule is for a week. I might go to this support group on Monday, but the next week I go to this one on Tuesday. Then group is not a person characteristic in that case. Between, yes, thank you. So more generally, if I just go with like a generic multi-level model of level 1 versus level 2 always goes with the word between. The only difference is between what? What are the levels? In this class, it's time within person, so level 2 is between person. If you come back next fall for the clustered version of multi-level models, it will be between and within cluster or between and within group. But level 2 between always works. What's another multi-level modeling generic word that I can stick in here? It starts with an M. I don't use this one as much, but you may see it. Macro, very good. Not to be confused with micro, which also starts with an M. Yes, what's for lunch today, by the way?
Yellow curry.
Yellow curry, okay. I was like, is it soup? Like, I could only see the yellow from here, but it looks good. And yes, totally fine if you eat and drink in this room. Just don't spill on the laptops, or then I get in trouble. So yeah, level 2, between, macro, those are generic words that work for this type of sampling design in which we're talking about differences in the upper level units. Specific to longitudinal data, we would have person characteristics, time invariant predictors, stable things. What if you measured something that you think is probably not stable, but you only measured it once? Then how do I talk about it? Not a trick. Is it time invariant still? Yeah. Yeah, because you can't know. If you only measured it once, too bad, right? You have to pretend like it's time invariant. But in that case, if it likely matters which occasion you measured it at, I would call it that in the name. So, parent behaviors when the child was 5, as opposed to just parent behaviors, for instance. Conditioning on when it matters, before, during, after, however you want to talk about it. I think that's all the words I can think of. Did I miss any? Cool. Moving on. How do multi-level models, as estimated in mixed or Elmer specifically, so I call these univariate because in these software packages, you denote one column as the outcome. So to me, that's one variable, even though conceptually it's multiple occasions. What do they do with missing predictor data?
They eliminate the rows with the missing predictors.
Say it louder.
They eliminate the rows with the missing predictors.
That's right. Rows with missing anything get kicked out of the model. Missing predictors or missing outcomes. Drop the whole row, exactly. Now, is that the same as list-wise deletion? Not necessarily, but it could be. So the distinction is at what level the information is missing. So if I have a covariate, for instance, that's measured at every occasion, but I didn't answer it at the third occasion, then my third occasion is gone. But what if it is a person level, level 2 person characteristic time invariant predictor, and I didn't answer it? Then what happens to all of my data?
Will be removed.
Yeah, bye-bye. And then I have an assumption of missing completely at random, which is exactly what it sounds like and is probably not viable in most cases. So yeah, multi-level models don't handle missing data. The way I would think about it is that it's better than least squares because it doesn't automatically do list-wise deletion of whole persons. But each row still has to be complete. So it does deletion of missing occasions, not missing people, unless you're missing a variable for all the cases a person has in which they're gone. So your choices in terms of what to do would be to select your sample to only the rows that are complete for everything that you're going to want to look at. That way your sample size stays constant. You don't have to worry about differences in -2 log likelihood, AIC or BIC, that arise from missing data. So that's one way to address the situation if you don't have a lot of missing data. If you do have a lot of missing data, then you might want to do something else. Some kind of joint likelihood estimation where you bring the predictor into the likelihood and pretend it's an outcome is probably the easiest. It then has distributional assumptions. So you would need a multivariate software package to be able to do that, something to where you can predict multiple columns at the same time, such as is within structural equation modeling or path analysis software. Otherwise, multiple imputation or Bayesian analysis or other strategies. Students have, at this point, usually asked me, is there ever going to be a class on missing data? And I'd like to say yes, but we don't have one planned. I think there should be, so you're not wrong to ask that question if that's what you were thinking. The difficulty in having, I think, a class about missing data is that it's always a solution in the context of a model, right? So I couldn't just talk about multiple imputation broadly without talking about how it would have to differ in a multi-level context. So you can't have a single level imputation model feed into a multi-level analysis model. That's not going to work. So any strategy that you would use for missing data would have to be in the context of the analysis you plan, which means that it makes more sense usually to talk about it in the context of the model as opposed to a standalone missing data topic. But what to do about missing data is an area of research, I think, that will never go away because people are constantly coming up with newer and better ways to deal with it. But the bad news is that, no, this doesn't handle it at all. It deletes cases. All right, any questions on that? All right, last one then. In growth curve models, or models for within-person change, what roles do the level 2 predictors play? What are they for, is the way I would phrase that. What's their purpose? And this plays into the answer for question 1 too, by the way.
My answer was that they help to adjust the growth curve.
Yep. They moderate or adjust the growth curve. So in the same way that when you introduce predictors into a model, the intercept is conditional on all the predictors equal 0. Like you have a reference value or group for your predictors. In these models, we're going to end up with a reference growth curve. So somebody who is at 0 on all the level 2 predictors, this is what their growth curve looks like. And then the fixed effects will describe what happens to it for people with different values of the predictors. It goes up, it goes down, it gets flatter, it gets steeper, and so forth. In terms of effect size, what can be tricky is figuring out which pile of variance a given level 2 effect is going to be targeting. As a general rule, you can say that it's going to target whatever random variance is in its level 2 equation. So if you put in a main effect of a level 2 predictor, that should reduce your random intercept variance. In a model that has both a random intercept and a random linear time slope, putting in predictor by time should explain the random linear time slope variance. If you had time squared as another random effect, then person predictor by time squared should explain that quadratic variance. So that's another way you can think about it, is that level 2 predictors in moderating the growth curve help us to understand why it is people differ from each other. So we can say, X% of the intercept variability is related to this predictor. Another X% is related to this second predictor, and so on. Can level 2 predictors have random effects?
No.
Nope, not in 2-level models. Level 2 predictors can be used to create heterogeneity of variance, which some people have technically said is a random slope, but it's not the same kind, and I don't want to use those words. No. Level 2 predictors cannot have random slopes in the traditional sense because there's no higher level for them to be random over. That rule is broken in 3-level designs or in level 2 designs with crossed random effects in which there's 2 different level 2s. But if it's just Level 1, level 2, like in this class right now? No. I didn't ask this question, but we talked about it briefly. What about heterogeneity of variance? Location scale models is the terminology for that. You can have level 2 predictors of heterogeneity. So it is possible to essentially ask the question, is level 1 within person variability different as a function of some person characteristic? So if I'm doing like a intensive longitudinal design, where I ask people about their negative affect and their stress and all sorts of things like that every day, you know, some people are sort of even keel, they don't vary very much, and other people are all over the place. Like that idea of even keel versus all over the place, that is another kind of individual difference that one can predict with level 2 predictors. Believe it or not, that is operationalized as a different kind of random intercept, but it's in predicting the residual variance. I know, it's a lot. That's next semester. I'm planting seeds, that's what we're doing right now. Just planting the seeds, that there's more to the story, but the big one that I want you to take with you is that the job of level 2 predictors is to moderate the growth curve, thereby explaining the random effects that define the growth curve. That's what they do. And that's it. All right, questions? Things I forgot. Things I can clarify. No. No is a perfectly valid answer. No, I'm good. Move on. Yesterday I had the chance to be in your shoes metaphorically because I went to a department meeting and the dean came and talked to us. And I felt very much like just sitting there listening to him, and he's kind of like, wow, you guys are you all tired today? I'm like, yes, we are. You noticed. He didn't ask the follow-up question, like, should I take this personally that everyone looks really tired? Because that's my question to you all. It's like, it's fine if you're tired, but if I'm annoying you, then you should tell me so I can stop it. I'll stop it if I can. I mean, to be fair, right? I'm always a little bit annoying. That's just me. But, you know, you're stuck with me. But you've made it this far. So there's that. But tired is okay. I understand, especially at this time of day. All right, then I will shut that off. I will pull up slides, and we can go back to talking about sort of conceptually how this process works, and then we'll see a very extended example with predictors and different kinds of growth models. So I think we were about here-ish, slide 17?
Yes.
Yes? Okay, thank you for that definitive answer. Here-ish is where we are here. So let me back up actually to set the stage for where we are or were, slide 15. Because that's actually one thing that I forgot to say that one of you said in your answers, and now I'm reminded staring at this slide. So another reason why it is helpful to build your unconditional model for time first. So that phrase, unconditional model for time, means that the only fixed and random effects you have in your analysis are for time. You don't have anything else yet. So that would be this type of model, for instance. This is a random quadratic, just as an example. We'll do some piecewise examples as well. Where at this stage, each level 2 individual difference placeholder, so the betas, I call them placeholders because betas are not parameters in this notation. They contain estimated parameters. They're like backpacks. They make it easy to carry them around. So beta 0i has a fixed effect and a random effect. Same with beta 1i, same with beta 2i. So the fixed part is what? We'll do a little review here. What's a fixed effect?
Time?
Time? Well, these I have 3 of them here.
Yeah.
Yeah, more generally, if I have a fixed effect, what is it?
Constant.
Constant, yes. Estimated constant. Estimated constant for what? Then gamma 0, 0 is my estimated constant that tells me my fixed intercept. So this is going to be my expected outcome when all the predictors are 0, which in this model is just time. So this is the time 0 expected value based on my growth curve. Likewise, gamma 1O. This is also a fixed effect, but it is a slope, not an intercept. So I would call this the fixed linear slope for time. And in this model, because we have time squared, I can't just say this is the linear slope for time, right? What do I have to say on the end of that phrase? This is the fixed linear slope for time, dot, dot, dot,
At time 0.
at time 0, yes. So what if you wanted a different one? What if you wanted to know what the fixed linear slope was, say, at occasion 1, or occasion 6, or occasion 9, or occasion 13, hypothetically? That's a cough, cough, homework 4 reference for those of you who haven't started yet. Yeah, I can ask the model to create a predicted linear slope for any other occasion. And it's always, what would the slope be at time 0 plus twice the quadratic coefficient time for the time that you want it for. So twice is the thing to remember there. And this one down here, what's this one, gamma 2O, going to be?
That's the half rate of acceleration, deceleration.
Yeah, this is half the rate of acceleration, or you could also call it the fixed quadratic slope. So if I just had this much in my model, then I would have 3 fixed effects and only 1 type of variability. But I don't. I've added the U's here. What are U's in this notation? What would you call them verbally? Yes, you would. And of the umbrella term random effects, there are 2 subkinds, intercepts and slopes. So U0 is my intercept. So this is how far off each person's intercept is from the fixed one. Likewise, U1 is a slope, deviation, relative to the fixed effect that goes with it. And U2 is a deviation slope relative to the fixed effect of gamma 2O. So you can think of these betas as variables, where the mean of the variable is the fixed effect, and the variability around that fixed effect is given by the U. So the average deviation from the fixed effect would be the standard deviation for each of these U's. Okay, with me so far? So those are the definitions. So this model says then how many ways do people differ from each other according in their growth curves? Basically, how many components go into making an individual growth curve here? Not a trick, I swear. 3, yes, you're all over it today. I'm going to point at you every time I want to hear the answer 3. How's that sound? There we go. So 3. So there's 3 different potential roles then that any time invariant predictor can play. So another reason why it is useful in practice to start with this kind of model is that this is our new baseline. This contains all of the variability in the intercepts, all of the variability in the linear slopes, and all of the variability in the quadratic slopes. So then we can see systematically by adding new predictors to each of these level 2 equations how much each of these random effect variances has gone down. Okay, and then E. Conceptually, what does E represent then? How would you describe it? This thing right here.
That's the residual variance, right? Time-specific deviation?
Yes, time-specific deviation. So E is not a variance, but it's here to remind us that we have a variance. It's the variance of the E's. So this is the time-specific deviation from each person's predicted growth curve down or up to where their actual Y is. So this is why are you off your line today, basically is the way I think of it. The only type of predictor that can explain why you're off your line today is time varying. Directly by itself, anyway, I should say. Okay. And I have a note here that you would need at least 4 occasions to fit this model, to have enough degrees of freedom to separate out 2 different random slopes plus a random intercept in addition to yield residual variance. How many parameters are in this model? Let's count them up. How many model for the mean parameters? How many red things? 3. Okay, three fixed effects is what I would call these. Fixed intercept or fixed slopes. How many level 2 parameters in the model for the variance?
6.
6, yep. 3 of these here, and what's the other 3?
Covariance.
Yeah, they're covariances. And where do they live? What's the name of their matrix?
G matrix.
G matrix, yes. In the SEM class, this would also be the matrix of the factor loading matrix. Psi, I think, that sound right? Or phi, maybe. I never use the words, so I don't remember what they are. But these would be the variances and covariances of the latent factors in that context. And so I've got 3 fixed effects plus 6 parameters in my G matrix, which is 3 variances and 3 covariances among my random effects. What am I missing?
The residual variance.
Yeah, and how many of those do I have?
1.
1. Could I have more?
Yeah.
Yes. So this notation implies there's only 1 residual variance that is assumed constant over time and people. And this notation is agnostic as to whether there's any residual covariances. So covariances, because they don't contribute to predictions, don't show up in these kinds of equations. So you'd either have to provide a G matrix or an R matrix or verbally describe that that's what you're doing with this. Either one, I think, is okay. All right, so then we started adding an example time invariant predictor to this. So we were here. So I'm adding in education level as a predictor that usually does not change if it's measured amongst adults, after some point at least, present company excluded. So 12 years as my 0 point so that my reference person has a high school degree in terms of the American schooling system. So I have added in 3 different slopes for education here, 1 into each level 2 equation. So if we start with the first row here, we're explaining how each person gets a different intercept. It starts with what's in common. So gamma 0, 0 here. We said previously that this was the expected outcome at time 0, right? Now it's also at education equals 0, which I have defined as being at 12. So this is the expected outcome whenever time 0 is for someone with a high school degree. Then gamma 01 is the slope for education, and I would call this the main effect. However, given that you have these other terms in here, I would have to say it's a conditional main effect or a simple main effect because it's specifically going to be at time 0. So this is the change in the intercept for a 1-unit change in education. With respect to the subscripts, do you remember why it's 0, 1 as opposed to anything else? Let's break it into parts. Why is this first subscript 0? Because of beta 0. Yep, the first number is which beta are you predicting in level 1. So all the terms that go with beta 0 start with the 0 in level 2. The second value is then which order of predictor in the level 2 equation. So another way to say this is that gamma 0, 1 is the first predictor of beta 0. So if I had another one in here, what would it be? It's subscripts. 02. And the next one? Oh, yeah, 03, 04, 05, etc. Yep. So then anybody who has a high school degree would have the same predicted intercept that is created by these 2 fixed effects working together. U0 then is still a random intercept, but the way that I would think about it is as random intercept left over. It's random intercept after controlling for education. And as I mentioned last time, at this point, textbooks tend to switch to the phrase level 2 residual because residual is the idea of leftover after being predicted, and I'm not going to do that to you because level 1 is residual in my vocabulary. So random intercept leftover is what I'm calling this. Unexplained random intercept variance, you could say something like that, remaining random intercept variance. So education here, this is a linear slope of education specifically. What if we hypothesized a nonlinear slope for education? Could we do that? Like education helps, but only up to a point, something like that? That could go right here too. It would be education by education as a predictor of the intercept. So the point I'm trying to make is that in the same way that we worried about whether times effects should be linear or nonlinear, in theory, every quantitative predictor, we should worry about that too. And the same strategies could be used to model nonlinear effects of predictors like education. So if you wanted to fit sort of an exponential sort of leveling off curve, you could log education and put that in as a predictor. Education squared would create a U shape where it's highest or lowest in the middle and then comes around relative to that point. Okay, with me so far? Next row then, beta 1. Beta 1 is going to tell me what?
That's the linear rate of change.
Yeah, this is how does each person get their own individual linear rate of change? It's now composed of 3 parts. Fixed slope. Because of time squared, still conditional at time 0. Because of this middle term right here, gamma 1, 1, it's also conditional in education equals 12. So this is the linear rate of change, instantaneous at time 0, for somebody with a high school degree. And then gamma 1, 1, we can talk about this 2 different ways because what this actually is a 2-way interaction between education and linear time. It's difficult to see in this type of multi-level notation, but if you pack all this stuff back into your beta 1 backpack and bring it up here, then it works out to be time multiplying by each of these 3 things. You can see it on the next slide more directly. So the top has the multi-level notation and the composite equation shows how what we were calling beta 1, when you unpack it, gets multiplied by time. So this term, gamma 1, 1, is education by time. Because education is measured across people at level 2, while time is measured across occasions at level 1, this type of 2-way interaction is called a cross-level interaction. So predictors that are measured at different levels, broadly construed. There's only 2 in this story, but there could be other combinations. So I can think of this 2-way interaction as doing 2 different things. Either way to explain it is correct. I can talk about how education moderates the linear change slope, or I could talk about how the effect of education changes linearly over time. Either one is fine. It's usually more convenient to go with the first one. Education moderates the linear rate of change. This is where terminology can get a little tricky. So the most correct way to say this is that this is the slope of education on linear change. Like that's what it is predicting as an outcome. Or you can say it's education by time. But where I've seen folks get into trouble with the wording is by saying something like, well, this is the linear effect of education, as opposed to the intercept effect of education. That is not correct enough. You can't say this is the linear effect of education because all 3 of these slopes are linear slopes of education. It's the linear effect of education on the linear time slope, more specifically. Both of them are linear. So gamma 1, 1 then is the increment to the linear time slope per unit of education. And with all 2-way interactions, there are only 4 things that can happen. So it's going to take my linear time slope and make it either more positive as education increases, Less positive as education increases, more negative as education increases, or less negative. That's it. It's one of those four. Likewise, U1 is now linear time slope deviations left over. So it's the remaining difference to get to each person's linear predicted time slope at 0 after controlling for their education. Okay, how are we doing? So has anyone here seen output from the HLM multi-level modeling package or in journal articles? Have you seen that before? Yeah, the way that that output is organized and often makes its way into journal articles uses terminology like, this is the intercept of the intercept, this is the slope of the intercept, this is the intercept of the slope, and this is the slope of the slope. And yes, that face is exactly right. That face hurts, right? Like, those words hurt. But because people talk like that, let me say this again from that perspective. So if I focus on just this quadrant of four things right here. This term right here is the intercept of the intercept. It's the jumping off point to how beta 0 gets made. Likewise, gamma 1O is the jumping off point to how beta 1 gets made. So I would call this, like within just this equation, this functions as the intercept, meaning where it starts from and what you would have if you had nothing else along with it. So gamma 1O, what I would call the fixed linear time slope, you could also refer to as the intercept of the linear time slope. So intercept of the intercept, intercept of the slope. Then these two, gamma 1O in the first row is the slope for the intercept, and gamma 1,1 is the slope for the slope. If you're going to use that kind of notation, adjectives are essential. The slope of the slope means absolutely nothing unless you say what it's the slope of, right? This is the slope of education predicting the linear slope for time, whereas this is the slope of education in predicting the intercept instead. It's nice if you can give them an equation and then give the notation in the table of your results along with the words. That way people can try to follow you. They'll either recognize the notation or they'll recognize the words or maybe both. And if you can help put it together, then people will be able to follow where the numbers would be interpreted and how they would be interpreted. Okay, how are we doing? Thumb sideways? Thumb sideways is a very good result. I'm happy with thumb sideways. It's harder to do poop emoji from in front of me, but yeah. I'm assuming that that's what the dean was feeling yesterday with all of us just sitting there. It's like, nah. Thumbs up emojis, even better. Yeah, we haven't decided on thumb sideways on the Zoomers, but if you find something that looks like thumb sideways, you know, that works for me. So then last one here. This would be another intercept of the slope and slope of the slope, except that this is the quadratic slope. So the quadratic slope starts with gamma 2O, which would be what the fixed quadratic would be for the reference person. Now, do I have to say that this is at time 0 or no? I do not, because time squared is the highest order term. So time squared is unconditional. The rate of acceleration is constant over time. That's the way you can think of that. So gamma 2O is not conditional on time squared. But gamma 2,1 then, this is how education moderates the quadratic slope. So education might be related to people leveling off faster or sooner than other people, for instance. And yes, gamma 2,1 is a three-way interaction. So this unit, by the way, this is the reason why chapter 2 of my book exists, is because when I first started teaching longitudinal models, things went off the rails when we started trying to interpret interaction terms, and I realized that folks generally had not been taught how to do that very effectively. So I wrote chapter 2 to just describe that process, which operates the exact same way if you have a single level regression model than if you have a multi-level model. because at this point it's just all about the fixed effects. The only catch is then trying to figure out for these different fixed effects of the same variable, which pile of variance they are targeting. And in this model, it's straightforward because I can just say each of these fixed effects is supposed to explain the U variance that's in its row. So the effective education on the intercept says why there's intercept differences. The effective education for linear time says why there's linear time slope differences. The effective education on time squared says why there's time squared slope differences. Easy peasy. Where it gets harder is if one of these is missing. All right, so here is the combined equation then. If I fill in the beta placeholders into just one thing, this is what it would look like. So this makes it a little bit easier to see that if you were to write out a single equation, each of the terms in the parentheses would get multiplied by time or time squared. It's up to you if you want to provide an equation for folks. I find them to be helpful when I'm reviewing papers. Whether you write it out this way or that way is up to you. Generally don't see both, but one or the other I think is helpful to provide. So these two, gamma 1, 1, and 2, 1, are cross-level interactions. Their job is to explain the random slope variance that goes with the term that they're included as. And that's the reason why we would need to have tested for the presence of U1 variance and U2 variance ahead of time. They go first, because that's the variance those cross-level interactions should be explaining. Yeah, go ahead.
In that slide, reasoning there in the second box, that's a typo, right?
Where's reasoning?
Of reasoning.
Yep,
That's
this
education, right?
is me stealing the slide from something else I did and forgetting to change that. Yep.
But that's the predictor.
It's education.
Right?
Yep.
Okay.
Yes. Please erase this word and put education on it, and I will fix the
Okay.
slide. Thank you. Yep, that's my bad. All right. Yeah, that's because I started stealing these slides from the workshop I gave last summer. So you'll recognize some of those if you came to that. So here is the exact same model as a structural equation model instead. The conversion back and forth happens as follows. First off, it's one circle per beta. So each effect that potentially has a fixed part and a random part goes in a circle. Random effects and latent variables are the same thing. The first circle here, which I have labeled level 2 intercept beta 0I, it is the intercept because I have taken the slopes relating how the intercept predicts each of my outcomes. So in this case, I have 6 outcomes. And I've taken that slope, which is called a factor loading, and fixed it to 1. So if you have a latent variable that equally predicts all of the outcomes, that's an intercept. Next to it is the linear time slope, and I know that it's a linear time slope because I made it that way by fixing the loadings that predict each of the occasions into the value of the time predictor that would go with them. So I've labeled these 0 to 5 so that they match the loading constraints. So these are fixed, they're constrained. They're things that I tell it, no, you're going to be 3, whether you like it or not. And then lastly, I know that this means quadratic time because I fixed the loadings to time squared. I know for which occasion the intercept is supposed to provide individual differences because it's the occasion that only it predicts where the other factors have loadings fixed to 0. So this circle is conditional on time 0, the first box here. I have this joint rounded rectangle thing here to convey the idea that each of these occasions has the same residual variance for. So that's constrained equal across the 6. The mean of the latent variables is the fixed effect. So the mean of the intercept variable, another way of saying that is that that's the fixed intercept. The mean of the linear time slope latent variable is the fixed time slope gamma 10, and the mean of the quadratic time slope latent variable is the gamma 20. Then their variances are the variances of the u's. So you can think of this as like the circle itself is beta 0. The variance that goes with it is the U0 variance. This circle itself is beta 1, has a variance of U1, and so on. Then the box. In SEM terms, boxes are for variables that you have in your data set. Observed variables, so I have level 2 education. And directed arrows are ways to convey a slope from the predictor to an outcome. So the label that goes from education to the intercept, or the path, excuse me, that slope is gamma 01. Education to linear time is gamma 11, and education to quadratic time is gamma 21. So when would I get the exact same results if I did it this way versus if we did it the way that we've seen in class?
If you don't have missing data in the predictor.
Missing data with respect to what?
In the predictor in education.
Yeah, so if education has missing values, then mixed and Elmer are going to kick them out. In this framework, I have the option of saying, let's pretend this box is actually an outcome, and I'm going to estimate a mean and variance for it, and then I get to keep people who are missing education. So that's what I mean by bringing it into the likelihood. You trick the software program into thinking it's an outcome by asking for its mean and variance to be estimated. Then you can have missing data under an assumption of missing at random, but then you're also assuming then that education has a normal distribution. What about estimation? What choice don't I have in an SEM framework? REML. No REML. So that means what with respect to sample size? I need more people. So this is not a good idea if I have very few people. But it is a good idea if I have missing data on education and I want to keep those cases. So like, this is the 6 of one, half a dozen of the other gesture, right? There's no universally good answer for everything. When else would this, let's see, in what other design consideration should I keep in mind? When might Elmer or mixed be a better option for me with respect to measuring time? In fixing these factor loadings to exact integers, what am I saying about my time schedule?
Everyone is measured at the same time.
Everyone's at the same time. The word for that I use starts with a B? Balanced. Yeah. What if somebody came at time 3.5? Too bad. You get to pick. Would you like to be in the 3 box or the 4 box? So then whether or not you can adjust your model depends on your software. To the best of my knowledge, in Levon, there is no option to fix it. You have to assume that it's balanced or pretend like it is. And in Plus, there is an option called T-scores that allows you to read in variables that are intended to be individually varying factor loadings. So they're not fixed at constants. They can be fixed at variable values. That's what's known as a definition variable. Again, the option is T-scores. So, cons for doing it this way. No residual maximum likelihood, which also means usually coupled with that is a lack of denominator degrees of freedom. So all of your walled tests for individual parameters are going to be based on z's or chi-squares. That means potentially higher type 1 error rates for small sample sizes. We also requires balanced time or the use of a definition variable to get around that if your software permits. Why would you want to do it this way? I can think of a couple reasons. To allow nonlinearity of a more flexible flavor. So latent basis models, I think we talked about that very briefly, maybe like a week or two ago. Does that sound familiar at all? Maybe? Everyone's looking down. Ish. So latent basis is the idea of letting it figure out what these loadings should be empirically based on your data. So you would nail down the first one and the last one and let the middle all get found as part of the likelihood estimation process. And the middle ones then would give you a sense of how much change had happened by that point. So if you nail down the first one to 0 and the last one to 1, you can interpret the loadings as the proportion of total change that had happened by each occasion. So I like latent basis models when there's some degree of nonlinearity, but I don't want to represent it with two different factors. So in this picture, could I have some other box that's an eventual outcome? Like I could predict what's going to happen to these people 5 years later, for instance, right? I could do that. But if I wanted to have the intercept predict some other box, the linear time slope predict it, and the quadratic time slope, what do you think is going to happen if I put time and time squared in as competing predictors? Do you think they'll have an overlap? You think time and time squared might have some collinearity to it? So then it gets tricky to say, well, change is related, but maybe the two are competing against each other and neither one is significant. So when it's more convenient to try to represent change with one variable instead of two, latent basis is a way to get that variable into something that's nonlinear. Also with respect to the E variances and covariances, your choices in the multi-level modeling packages tend to be either homogeneous or heterogeneous. So either the E variance would be the same across occasions or they'd all be different. In this type of framework, you could go in and say, you know what, I'd like the residual variance at time 5 to be separate, but the others can all be the same. You can make those sorts of like custom fits. Likewise, if you had an extra relationship between, say, occasion 0 and 1 that wasn't there before the others, you could just let that one be there, just like a regular old residual covariance. The true motivation for fitting structural equation models with these types of data would be to replace these lower boxes with circles. So if you had a measurement model where inside each of these boxes, say, was multiple items, you could fit a latent variable for each occasion and then look at change in that latent variable rather than an observed variable. So I hope to show that to you next semester as well. All right, so here's some code then. This is what it would look like in M+. So either fit a quadratic model on the left or the latent basis model on the right. And the difference here is the stars, where the loadings used to be fixed. And here is the same code in Lavon to do the SEM. So these codes would go with this picture. The code on the right is the latent basis version of the same model. And that's what that would look like. If I wanted to do multi-level SEM, this is the newest, coolest thing. Whatever. I call it multivariate multi-level because it still doesn't have a true measurement model to it. But in that case, you'd go back to long data, and it would not be any different than what we were doing in Elmer or mixed, except for the lack of REML and lack of degrees of freedom for the denominator, which still means problems for small data. So not better in this case. Time-varying predictors is the reason to switch to this framework, not time as an observed predictor. And this is what it would look like in M+, by the way. So this is something I haven't done in either class, the multi-level SEM syntax between within. It's analogous in Lavon, but it doesn't have random slopes, and so we won't be able to use most of it in Lavon next semester, but this is what it's going to look like for the record. All right, 133, how are we doing? Yeah? Hanging in there? Questions or things that you want me to say again or say differently? Zoomers, thumbs, thank you. All right, then the next section here is introducing you to a controversy. Dun dun. Yes, nerds fighting against themselves about the proper way to fit models. That's what I'm giving you here. So in terms of effect size, if I have a model that looks like this, where education is a predictor in all 3 of my level 2 equations, the easiest way to talk about how each of these slopes is contributing to the model is to measure the change in its corresponding random effect. So the formula for pseudo R² uses a baseline model in which there are no level 2 predictors. So over here on the left, this would be as much U0 variance, as much U1, as much U2 as there is to be had. That would be the first spot here, the random variance for the model that has fewer parameters, minus what it is after putting these fixed effects in, and then dividing by what it is from before. So you would have 3 separate values for pseudo R square, one for each of these. And if U0 variance went down, I know it has to be because of this slope, gamma 1, O1, excuse me. If U1 variance went down, I know it has to be for this one. And if U2 variance went down, I know it has to be for that one. Cool. No problem in that. So here's the controversy. We said earlier that we have to get our model for time right before we do anything else. Remember that part? Okay. So what if I go through all my process, I figure out that I need a quadratic growth model, but there's no evidence, not enough evidence, that I have individual differences in linear change or quadratic change. So if I have, say, a fixed quadratic random intercept model, first off, is that okay? Could I end up with that as a possibility? Fixed quadratic random intercept. You don't think so? No?
Maybe, yeah.
Does it break any rules? Let's put it that way. It doesn't break any rules.
No.
What would it look like? What type of trajectories would fixed quadratic random linear get me? Yeah, this is a gesture question. Bendy, right?
Yeah.
Some kind of bendy, but parallel bendy, right? Because intercept differences mean constant differences. So some sort of parallel but bendy curves. So that's okay. That's what you may end up with if you don't have a lot of people, because you need people to have sufficient power to detect random effect variances. So let's say then that I'm the data analyst on an NIH project. They just paid us $5 million to go cure cancer or something, you know, as one does. And there's not a lot of people with cancer in my study because, you know, cancer patients are busy, right? They're trying to survive the rest of their treatment. So I don't get a very large sample. It looks like I have my fixed quadratic random linear model, and my primary interest is in whether or not my new treatment made people better. Can I still answer that question? Because there's 2 different possibilities here. Some people would say, well, no, because you don't have any evidence that people change differently. So why would you go and ask if the treatment group grew more if people don't change differently in the first place? The rest of us would be like, but I have $5 million and you're telling me I can't answer my question? No, that's dissatisfying. So there is somewhat of a controversy in this situation where if you're interested in the effect of a level 2 predictor, but you don't have random variance in some of the terms, does it make sense to still test these cross-level interactions? Some people would say no, because if the level 1 effect does not vary randomly across people, it does not make sense to see if it varies as a function of group or education or gender or anything else. It doesn't vary, period. You're done. Game over. And to back up that supposition, they would point to studies that show that if you fit these cross-level interactions without the U that goes with them, your type 1 error rates are way too high if the U should be there and it's not there. The rest of us are like, but, you know, power and type 2 error, and it could be fine so long as you test for the U first, right? So putting yourself into this latter camp, which I am a member of, requires some new vocabulary. The term I want to introduce you to is systematically varying. So there's 2 vocabulary words we already reviewed, right? Fixed and random. Fixed means everybody gets the same. Like if I say fixed quadratic without a random quadratic, everybody's bendy is the same. Random means everybody gets their own. So you can think of those as like endpoints on a continuum here. Somewhere in the middle is a possibility that we haven't discussed yet called systematically varying. And that would be the idea that people need different slopes as a function of a predictor, but not otherwise. So systematically varying would be like, yeah, the control group slope should be different than the treatment groups, but there's homogeneity within group after that. So there's only 2 different slopes, not, 50 or however many would be implied by your sample size. So systematically varying is the middle ground, that everybody's slope is different deterministically as a function of some covariate, but not randomly otherwise. So in this example, we would say that people who have the same education level have the same growth curve. There's no difference among people who have 12th grade education. There's no difference among people who have 16th grade education. But there is a difference between those 2 groups of people. So here are the possibilities of what can happen if you go through the steps of testing for random slopes first and then deciding to put in level 2 predictors. So let's say that group, like control versus treatment, is what I care about, and my focus is whether or not it should moderate time. One situation, if I find the random slope for time I initially test and it's not significant, I test group by time anyway and it's not significant, then I would say that the linear effective time is fixed. Everybody gets the same, the end. Doesn't vary randomly across people, doesn't vary deterministically as a function of group, it's just fixed. But what if I did find a significant group by time interaction? Then I use my new label. It's not that everybody needs their own, it's that the treatment group needs one and the control group needs the other. So there's 2 different slopes. It could also happen that you thought you had a random linear time slope, but then you put in group by time and it went away. That is the best case scenario. What that would mean is that you thought that people needed their own, but it turned out the reason they did is all because of treatment group. And once you put that reason in the model, they don't need their own anymore. Another way of saying it is that you would have accounted for 100% of the linear slope variance with your effective group. You win. I've never seen that happen unless it's a really tiny slope variance to begin with. The last row is if there were a significant random time slope and it stayed that way even after you put in group, then we would still call it random. So yeah, maybe it is that group predicts it, but there's still some information left over. Why we don't know why people need their own slopes yet. Still random. So the addition of that vocabulary phrase then is used for level 1 predictors. They can be fixed, random, or systematically varying. Level 2 predictors can only be fixed or systematically varying. They can't be random. All right, 143. How are we doing? Doing okay? Yeah, so this is, like I said, controversial. You can find different textbooks talk about it. This is one of those things where I wrote a paper on it. It ended up not being reviewed well, and I put it in a drawer and haven't gone back to it. So I need to go back to that because this was actually something I found to help solve the problem, was to use slope reliability as a cutoff for when you keep your random slopes rather than a significance test. That is, you would use effect size instead of significance. I know that's a crazy idea, but it actually, in the simulation that I did, it worked pretty well to reduce type 1 error rates in this situation. So I would say yes, systematically varying effects are cool so long as you've done your due diligence and tested the random slope that goes with them first. And you keep it so long as it has at least some degree of effect size. There we go. Ta-da. All right. Let's see. It's Happy Garbage Day. That means I don't say have a good weekend. Although I really wish I could. Instead, I say office hours tomorrow. I hope to see you Thursday. Let me know if you need anything, okay? All right. Hang in there, folks. Thanks for being here. Bye for now.